Manabendra Bera to chair this session. Dr. Manabendra.
Thank you, Professor Banerjee. So we are going to start today, and today we'll be talking about measurement-induced collapse and the role of observer. And the first speaker today is Professor Howard Mark Wiseman. He's an Australian theoretical and quantum physicist, notable for his work on quantum feedback control, quantum measurement, quantum information, particularly quantum steering, open quantum systems, the many interacting worlds, interpretation of quantum mechanics, and other topics in quantum foundation. From 1996 to 2009, he held Australian Research Council Research Fellowship. He is currently a physics professor at Griffith University, where he is the director of Center for Quantum Dynamics. He is also an executive node manager in the Center for Quantum Computation and Communication Technology at ARC Center for Excellence. So with this, I will now invite Howard to start his talk. Please go ahead.
Thank you, Professor Bera. Can you hear me?
Yes. So you may need to share your screen. Yes. I'm waiting for that.
Oh, that's good. Okay.
Yeah, please go ahead.
Okay. Thank you. So yeah, it's a great pleasure to be invited to talk at your conference on 100 years of quantum mechanics. It's a pity, yes, I can't be there in person, but yes, I have been in India early this year and will be in India again early next year, but I'm afraid not for this one. So, so my topic for this talk is the local friendliness no-go theorem, and I want to highlight a couple of co-authors in particular, although there are other people that I'll mention as we go along. And those are Eric Cavalcanti, and who's with me at Griffith University in the Center for Quantum Dynamics, and also Eleanor Riefel, who's at the Quantum Artificial Intelligence Laboratory at NASA. And yeah, this work is supported by, what I'm going to present is mainly from two papers. Whoops, is it going to work? Oops. There we go. So one is this paper from a few years ago. So with myself and Eric, does my cursor show up on the screen? It looks like it does. Yes, at least it does to me. And Eric, but then a lot of other authors as well. And partly that's because this was an experimental as well as a theoretical paper, which I will talk about. But then also this more recent paper with just Eric and Eleanor, which I'll talk about later. So you might be a little bit confused because this is a collapse session. Why am I, and we're supposed to be giving a sort of overview talk, so why am I saying that I'm going to focus on two particular papers of mine? Well, one reason is that I think they are actually an important development in quantum foundations, which is related to collapse. And so, for instance, it was one of the first paper was recognized, one of three papers that won the Paul Ehrenfest Quantum Foundations Award in 2023. Again, you might say, well, why don't I talk about all three of them? And I guess the answer to that is I've only got 40 minutes or whatever. And I think actually the paper that I'll talk about is the easiest to understand of these three. It gives the clearest message. So that's my justification for concentrating on my work. So I guess I wanted to make a few other points in introduction. So unlike some of the talks which I attended yesterday, I'm not going to be presenting my preferred solution to the quantum measurement problem or the quantum reality problem. And I'll leave you guessing about whether I even have a preferred solution. If you can't guess, then I feel that I've done a good job, because what I'm really trying to present here is a theorem, and it's a theorem that applies to any interpretation, and in fact, I'd say rules out some interpretations or these things that people think are interpretations. But I will, more than so than when I usually give this type of talk, I will expand some more on the particular relation of the theorem to collapse theories, because I think there are some particularly interesting things to say in that. And I'm also going to begin with the context of collapse. And just to highlight it, so I actually do have 1 or 2 papers on collapse models. So this is a fairly recent one with Antoine Tilloy, but I'm not actually going to talk about that work at all, but just to let you know that there is other stuff out there that I could have said about collapse models. Okay, so here's an outline of the talk. So that was sort of the pre-introduction introduction. Now I'm going to be moving into the introduction, and then talking about the original theorem and the experiment in the 2020 paper, before going on to the more recent work, which we call a thoughtful local friendliness no-go theorem, for reasons that will become obvious, and then I'll conclude. Okay, so an introduction. So you saw Wigner's friend, I think, and I can't remember what the title was exactly. No, okay, local friendliness. At least the word friend appeared, and this word friend comes from Wigner's famous 1961 paper, or essay, perhaps more appropriate to call, which was on collapse and the observer's role. So exactly in the context, exactly fitting in the theme of this session. So he wrote this essay called Remarks on the Mind-Body Question, and I think it's worth looking at this extended quote from this paper to see, where this friend comes from. So Wigner writes, it is natural to ask about the situation if one does not make an observation oneself, but lets someone else carry it out. What is the wave function if my friend, and so I've highlighted this because this is where Wigner's friend comes from, what is the wave function if my friend looked at the quantum object? The answer is that one could only attribute a wave function to the joint system of friend plus object. And there's that type of superposition wave function that he's considering. So psi is for the friend, say, and chi is for the object. And he says that this follows from the linearity of Schrodinger's equation. But then he goes on to say, this appears absurd, but because it implies that my friend was in a state of suspended animation, that is, in the superposition of having observed one thing and the other, before he answered my question about what he saw. And Wigner's conclusion from this is that it follows that Schrodinger's equation cannot be linear if it is accepted that my friend, commas, has the same types of impressions and sensations as I. So in other words, he just does not think it can be the case that a friend could be in a superposition like this if he's going to treat the friend in the same way that he would treat himself. Okay, so that was 1961. It certainly wasn't a universally accepted idea back then, but just to summarize what he's saying in this 1961 is that this is at least the way I read it. He's saying that measurement implies collapse of the wave function. You can't have a measurement without collapse of the wave function. And second, that human level sentience is sufficient for this to occur. So he's not necessarily saying that it is human level sentience which causes the collapse, but he is saying that if you have human level sentience, then there must have been a collapse. You can't have that in superposition. And sometimes this is called the Wigner von Neumann view. And yes, von Neumann wrote some sort of similar things, less detailed. And what I want to say here is that this may be true. This is a possible way that the world could be. However, I would say that it's probably a minority view amongst physicists in general. And part of the reason for that is that there have been advances in quantum interpretations and just generally being open-minded to more different types of quantum interpretations. But more particularly, there have been advances in experiment which rule out natural classes of collapse theories, which I think you've heard about earlier in this conference. But lastly, also advances most recently in quantum technology, especially in quantum information technology. That means that, as I said, that I think most scholars would at least doubt, or some of them would definitely just dismiss, both of these ideas here, both that measurement implies collapse and that human level sentience is sufficient for collapse to occur. So in particular, for a lot of people, it's now seen as plausible that Schrodinger's equation is universally valid, in other words, that there is not collapse and of any sort, and that measurements are just processes like any other process, and so could be reversed by sufficiently powerful technology. Okay, so again, I'm not saying that this is true. Like I already said, that the above may be true, but it also may be true, you know, that this is completely wrong, right? That in fact, there's nothing special about measurements, or there's nothing indeed that leads to collapse of Schrodinger's equation, collapse of the wave function rather. And so yes, this is an idea that I want you to keep in your mind going forward, is that this is at least regarded as plausible by many physicists now. Okay. Right, so the other key bit of background that I want to explain before getting on to the new theorem is also from the 1960s, but rather than just a sort of musing essay, this is an actual theorem, Bell's 1964 theorem, which I'm sure is familiar to almost everybody. This is the paper. And so I'm just going to put up the statement from the conclusion of this paper, which I think clearly explains what the theorem proved, and that's this, that the statistical predictions of quantum mechanics are incompatible with separable predetermination. Okay, what does he mean by that? That is, in any theory in which parameters determine the results of individual measurements, so that's what he clearly means by predetermination, then this other part must be false, right, if it's incompatible with the conjunction of these. So in other words, the lack of separability, or which we commonly now call lack of locality, is that there must be a mechanism whereby the setting of one measurement device can influence the reading of another instrument, however remote. Okay. So I put this part of the text in brown because I want to make a distinction between, in Bell's theorem, what are just assumptions about what we could test, and what are what we might call metaphysical assumptions about the way the world could be. And so the point is that the locality or separability and predetermination are assumptions about the way the world might be, but the statistical predictions of quantum mechanics is just something which we can go and test. Okay, and so since 2015, we could actually, instead of that Bell's, so at least since 2015, one could argue maybe even earlier, one could replace this assumption about the statistical predictions of quantum mechanics by just the results of Bell experiments. Okay, we could say that the results of Bell experiments are incompatible with these two metaphysical assumptions. There's two assumptions about the way the world might be. Okay. Now the reason I've highlighted one of these in this sort of greenish, yellowish green color is that this is the one that, again, most physicists would say is the natural one to give up, rather than the assumption of locality. But I'll return to that idea later. Okay, so that's the background, the two basic sort of background. And then it was Charles Bruckner, who was the author, sole author on the first paper that was listed in the Ehrenfest Award 2023, who put these two ideas together for the first time, as far as I know. So that was this paper published in 2018, essentially combining the ideas of Wigner and Bell. So the idea is to incorporate Wigner's friends into a Bell experiment, and the intuition which Bruckner had was that this assumption of predetermination, which is the one that most physicists would say Bell's theorem is indicating us to get rid of, because it's not a feature of quantum theory, right? His assumption is that we could not have to make that assumption if we have friends and have their friends' observations play the role of hidden variables. And I think I hadn't actually mentioned hidden variables, but probably you're familiar with that idea of hidden variables as being the things that do the predetermination. Okay, there was a hiccup in that. So that's Bruckner's intuition. The execution of the paper was a bit flawed because the assumptions didn't actually. He ended up formulating in a way that was equivalent to assuming predetermination, which is a bit of a problem. But then, luckily, we found a new theorem using a much weaker formalization which essentially worked in the way that I think Czeslaw Bruckner's intuition wanted it to work. So in other words, we found a new theorem using a weaker formalization, and particularly using weaker assumptions than Bell. And so that's what I want to go on to explain in the second half. Okay, so this is our theorem and the experiment that went with it. So first of all, the theorem. So before we get to that, what I want to do is give you a more fine-grained version of Bell's theorem, because I think this will help appreciate the difference between Bell's theorem and our theorem. So this is my version of one of my preferred versions of Bell's theorem. Definitely, I think it sets out the assumptions more explicitly and some of the assumptions that were missing in Bell's original paper, and just in a different way. Okay, so this is my preferred way anyway. So we have an assumption of so-called, pardon me, interventionist causation, which sounds complicated. It's more or less like a free choice assumption. But specifically, this is a free choice assumption expressed in terms of cause and effect. Okay, so the assumption is that a free choice is uncorrelated with any set of experimentally relevant events unless it is a cause of at least one of those events. So you don't, so free choice is not just for any arbitrary reason correlated with something in the experiment. We would actually have to cause something going on in the experiment in order for it to be correlated with it. I think that's a pretty intuitive understanding of free choice, but we give it this technical term to say explicitly what we mean. You might worry about, well, I'll finish, I'll save the next one. Second one, relativistic causal arrow is just that, so this is like relativistic causality, but we make it, again, very particular. Any cause in an event is in its past light cone. Again, I think that's most people's understanding of how causality works in relativistic theory. And yeah, so that's our assumption. So I think at this point I might say you might be worried that I haven't defined what I mean by in a cause. And it actually doesn't matter. I've used this particular font for cause because these assumptions work together to give you a particular conclusion without having to actually give any formal definition of what a cause is. Okay, we just have to realize that a cause is an event, and by an event, I think something which can be localized in space-time to a particular, a smallish region. Okay, third assumption: absoluteness of observation. Any observation is an absolutely real event, not relative to anything or anyone or any world. And so this is, this is like the single worldedness, which Adrian Kent talked about in his talk, I remember yesterday. So it is actually a necessary assumption for Bell's theorem. We have to believe that the measurement results are real things that happen in the world. In order to come up with the conclusions for Bell's theorem, we need to believe that. We can't believe that well, my results are just relative to me and your results are measured relative to you, and we can't conclude anything about anything that's happening in the world if we do that. So we actually do need this assumption for Bell's theorem. Next one, Reichenbach's principle of common cause is a fairly long one. I'll quickly read it. If two sets of events are correlated and no event in either is a cause of any event in the other, then there exists a set of common causes such that conditioning on the common cause values removes the correlation between the others. So essentially, this is just saying that correlation requires causation, either direct causation or causation by a common cause. But you don't get correlation happening for no reason. That's Reichenbach's principle, dating from the 1950s, I think. Okay, and then finally, this one in Brown. Is just that Bell correlations, in other words, the statistical predictions of quantum mechanics, exist for loophole-free Bell experiments. And as I said, so this one is not a metaphysical assumption. This is just an assumption about what we can see in experiments. And as I said, at least in 2015, we don't even have to list it as an assumption. We can say that, this is, we have already seen this, but I want to list it here as an assumption because, I want to imagine a situation before we had maybe done those loophole-free experiments. Okay, so which of these assumptions will we give up, right? We know we have to give up one of those assumptions. We know we can't give up 5 because we have actually seen it. Well, most physicists, so there is no assumption of predetermination anymore. But if you ask, well, what's the thing that's most like predetermination? It's actually this one here, Reichenbach's principle of common cause. Because again, in quantum theory itself, this is not the case, right? We can get correlations in quantum theory without there being any event that we can, there's nothing in the theory where there's a value of some variable that we could condition on in order to remove the correlation from an entangled source, for example. So this, so again, with this color, this is probably what most physicists are going to reject. Okay, so now I can finally get on to the new theorem. So this is what we call the local friendliness no-go theorem in this paper, but the version I'm going to present here is closer to the one in this paper by Eric and me from a few years, or 1 year later. Okay, all right, so the first 3 assumptions are exactly the same as in Bell's theorem. This free choice-like assumption, relativistic causal arrow, and absoluteness of observation. Then we simply do not make the assumption of Reichenbach's principle of common cause. So the thing that most physicists would say is the thing to give up, we are not making that assumption. However, we do have a more powerful assumption, which is this experimental or technological assumption, which we call barrel correlations with superpowers, or I'm calling it that here for this. Yeah. And what do I mean by that is the superpowers is something that a super observer has, and particularly the super observer has to be able to approximately reverse the evolution of an observer. That is the friend. And you might say, oh, well, I don't believe that. And that's fine. You might not believe that, but we don't know that it's false, right? This is, again, something that we can experimentally, in principle, if we have a powerful enough super observer, we can see whether this is actually true or not. Okay, so that's what I said here. It's not a metaphysical assumption. Its truth is an empirical matter for a given super observer and a given observer, at least. So, right, so this is why we say that it's the assumptions are weaker. The metaphysical assumptions are weaker than those of Bell's theorem, because we are not making this principle here, this assumption here of Reichenbach's principle, but we are assuming that we can do experiments which are much more difficult than in Bell experiments. Okay, whoops. So to explain briefly how this works, I think I have to go very fast, but as I said, we're imagining that we have, we're including being as friends in a Bell setup. So we start off with 2 parties who are going to be the friends, so Charlie and Debbie. So they share an entangled particle, and then they each make a measurement on that entangled particle in their one particular basis that they're going to measure. Now I'm going to concentrate on one side, so not worry about Debbie for the moment. So Charlie is the friend of Alice. So Alice is the super observer, and she can do 2 things, or more than 2, but like essentially 2 different things. One, if she makes a free choice of 1, that's her setting 1, she simply asks Charlie what he observed from his experiment, and she records that as her result in that run of the experiment. On the other hand, this is where the superpowers come in. If she chooses some other setting, what she does is press a button on a machine that inside Charlie's lab runs time in reverse, essentially, so just locally inside, so that the measurement that Charlie had made becomes undone, and Charlie is now disentangled from this qubit, say. Then Alice simply discards Charlie and takes the qubit and makes her own measurement on it in whatever basis she wants. So those are the 2 different things that Alice could be doing in the experiment. And so, yeah, in space-time, we're imagining that we have, the things that Alice is doing is over here, and the things that Bob is doing is over there, and Charlie and Debbie are closer to Alice and Bob like this. How do the assumptions work? So the absoluteness of observations tells us that Charlie and Debbie really saw outcomes, right? We're treating them as observers. So C and D the outcomes that they got always exist. So there exists a joint probability over P, A, B, C, D for whatever choices that Alice and Bob make. Okay? That's what the absolutes of observation means. But the relativistic causal error plus independent causation tells us something about what effects X and Y can have, and basically that they can only be correlated with things in their future light cone, right? So, yeah. So X really can only affect A and Y can only affect B. And so that leads to these constraints on that joint probability distribution. And we call this phrase local friendliness for the conjunction of the constraints which you get from these assumptions here, okay, from these metaphysical assumptions. Now, I haven't, whoops, there we go. Okay, so here's the scenario again. So we have the Charlie and Debbie friends and Alice and Bob. So from these local friendliness assumptions, those constraints on the probability distribution which follows, and crucially the fact that in this setup, right, when X equals 1, Alice is just finding out what C was, and when Y equals 1, Bob is just finding out what D was, because they just asked them. Right? We can derive what we call the local friendliness inequalities in analogy to Bell inequalities. And these are just correlations that the outside observable probabilities, the probability of Alice's result and Bob's result giving their settings, there are constraints on those correlations. Okay, so the local friendliness inequalities do not involve anything to do with C and D. Right? They're purely on these correlations that can be verified by any party, like who's at the level of Alice and Bob. But then the crucial thing is we showed that if the appropriate superpowers exist, even in an approximate sense, so that the probability that Alice and Bob undo Charlie and Debbie, undo their measurements, that these probabilities are approximately the same as if there had never been Charlie and Debbie there in the first place. If this approximate reversal, even approximate reversal is possible, then we can violate these local friendliness inequalities. And that means we have a new theorem of experimental metaphysics, as we could put it. A new theorem in which you can do experiments and test some metaphysical assumptions, but crucially, they're weaker metaphysical assumptions than in Bell's theorem. So it's more fundamentally more interesting experiment in that sense. Okay, so because it's an interesting question, we did an experiment, right? I'm not going to go through all of this. I'll just say we violated a local friendliness inequality by 17 standard deviations. So, hooray! So why are we not famous for having done that? Well, okay, because each friend in our experiment was just a single qubit. Okay, each system that we were treating it as observer was just a single qubit. So in fact, just 2 paths for a single photon. So that's why we were able to do this experiment without actually having superpowers. I mean, my experimental colleagues are very good, but I wouldn't say that they have superpowers. So this raises the question, so can a qubit be a friend? Can a qubit be a friend in the being the friend sense? So some people actually do. Some other of our experimental colleagues have stated that yes, it can. However, we certainly didn't state that it was, and my personal opinion is no. And so that's why we called our experiment a microscopic proof of principle version of a local friendliness experiment. So that raises the question then, how to do a real experiment. What is a real experiment? What makes a friend, inverted commas, into a real friend? So we didn't give any criterion in our 2020 paper for what would make a friend a real friend. There are many different things one could say, but for this talk, I want to move on to what I think the most convincing answer is, and that's to go back to what Vigna said, a being with the same types of impressions and sensations as I. That's what Vigna meant by a friend, and I think that's what the most convincing Vigna friend, local friendliness experiment would be. Okay, but now this is a problem because, how do we even know that anything is sentient? I don't, that's a philosophical question I don't have an answer to, but as a fallback, instead of talking about sentience, we could talk about thoughts. because at least since Turing argued it, it's much easier to accept that we could have a machine that has thoughts, okay? And if we're talking about a machine with thought, a machine, then that's something that we could imagine being unitarily reversed. But what that means in practice is we have to have an artificial intelligence realized on an enormous fault-tolerant quantum computer. And so that's what I see as being the route to the most convincing real local friendliness experiment. And so that's what we talked about then in this, this other paper published last year with Eric and Eleanor. So a thoughtful local friendliness no-go theorem, a prospective experiment with new assumptions to suit. So I'm going to start with the experiment and then move on to the assumptions. So here's a sketch of the experiment. So it turns out, I showed you before with Charlie and Debbie, you don't actually need Charlie and Debbie. You can actually get, not the same set of inequalities necessarily, but you can get inequalities which can be violated with only one friend. And so that's what we proposed here. And so also instead of calling the friend Charlie, we called him Quali, which is a little bit of a joke, but you can try to figure out what that is. So Quali is a human-level artificial intelligence running, as I said, on a very large and very fast universal quantum computer. So could just be running a normal artificial intelligence algorithm, but has to be running on a computer because Quali has to be able to take in a qubit and make a measurement on that, like observe that qubit without, well, simply by processing the information that exists in that qubit. Okay, so taking in that qubit, looking in inverted commas at the information in a particular basis, thinking about that information, etc. That's what we mean by observation in this context. Nothing that can't be modeled by a purely unitary process. At least that's what most people would expect from a quantum computer. So we've got a slightly different setup here. We have that Quali observes this qubit and then sends whatever result he sees in a sealed envelope out towards Alice. And then Alice decides either to open the envelope and see what's written inside, or to return the envelope to Quali, at the same time making the quantum computer, the whole system, run in reverse, so that at the end of it, this qubit would come out as being as if it had never interacted with Quali, and can go on to Alice, who can measure it in whichever basis she wants. So these are the two different ways that Alice can get her result A. Meanwhile, Bob just makes a simple measurement on his qubit and gets result B. Okay. So here's a space-time picture of all of those processes happening. And if Ila Ying is in the audience, I'll give a shout out to her for making this picture. So just some further remarks on how this experiment would actually work. So the idea is we need Quali to actually pass the Turing test, so to essentially to show intelligence at the human level, and to be able to respond as fast as a human when we're in conversation. So we make some estimates about how fast and big a quantum computer would need to be in order to do that. And I think that surprised us at how demanding those requirements are. So I think I'm probably safe to say that this is not going to be achieved in my lifetime, but it could be achieved in the lifetime of some of the people in this room. So I hope that prospect excites you. Okay, so Quali then, once we're convinced that he has human-level thoughts, etc., he would have to be completely isolated for roughly 1 second, the time it takes to observe the input qubit and think about his result, compose a message, and send it to Alice. And then in some runs, his evolution would be reversed. So at the end of that, he would have no memory of having ever measured the qubit in the first place, but he wouldn't lose any of his other memories. It would just be that 1 second of time which would be reversed for him. But even just reversing 1 second of time, I think we have to take Quali seriously as a party in this experiment, not just a system. But if we're going to treat him as a friend, if we want to think that his observations potentially have the same qualities or the same level of reality as human thoughts, then we have to, for example, get ethical approval from quality to undertake an experiment like this, which would require, you know, erasing his memory in some runs of the experiment of roughly 1 second of memory. Okay, so as I said, those are just some remarks. But if we can do all of those things, then we could, if the experiment worked as most people probably predict it would, then we would rule out the metaphysical assumptions and the local friendliness theorem. But we wanted to be more specific in this paper. So this was my goal of writing this paper, is to set out a slightly different set of assumptions, again, to really highlight what we get from this local friendliness theorem. So again, the first two assumptions are the same as before: interventionist causation, relativist causal arrow. But now, instead of jumping straight into absoluteness of observations, I'm going to talk about the absoluteness of human thoughts to begin with. So we're going to say here, any human thought supervenes upon an absolutely real physical process. So there's the absoluteness, right? Real physical process in the obvious bounded space-time region. So in other words, in my brain and in the time that it takes me to, you know, have that thought. Okay. And now I want to introduce friendliness as an explicit assumption in the local friendliness theorem for the first time. So friendliness to human-level artificial intelligence. So this says, if a party passes an open-ended Turing test, then they have thoughts, and any of their communicable thoughts, remember the qualia is actually communicating his thoughts in this experiment, any of their communicable thoughts is as real as any communicable thought of a human. Okay, so that's, yeah, so we sort of split up the absoluteness of observations into, yeah, these two parts with an explicit assumption of friendliness, as I said. Then, in terms of the technological assumptions, I've split this up into two as well. So one is just that human-level artificial intelligence is possible, and we're not quite at that level yet, but I think most people would agree that we're getting scarily close to that, and so I think that's a very plausible assumption. And then the last one is that universal quantum computing can be done at the very large scale and very fast processing speeds that is required. So in other words, when I'm not talking about superpowers anymore, right? These are, it's not fantasy, it's science fiction, okay? It's not something we know for sure we can do, but it's something that we can speculate that could very well be possible in the medium to long-term future. We also require quantum communications to do the space-like separation, but that's probably a trivial requirement compared to the universal quantum computing. Okay, so again, so this is not exactly the way you'll read it set out in this paper here, but it's sort of simplified from that for this talk. Okay, so let's, so what we can say, to be specific, one of these assumptions has to be wrong, because the conjunction of all these leads to a contradiction, right, through the local friendliness inequalities and their violation. So basically all the first four lead to the local friendliness inequalities, and then the 5 and 6 say that we could actually do an experiment which would violate those inequalities. And therefore, it's not possible for all of these things to be true. So let's look at, so any proper interpretation of quantum mechanics must reject one of these assumptions. And ideally should have a clear answer about, it should have a clear answer about which of these assumptions, or perhaps more, it's actually rejecting. And I think this is a useful thing to do. So here I've given, so 6 interpretations confront 6 assumptions. To say which one are they giving up. And so I've actually got 3 different types of collapse models here, and what they give up, which I'll talk about in more detail on the next slide. But yeah, I think this is interesting that we can't just say, oh, a collapse says this. It really depends on what sort of collapse one is talking about. And so the sort of assumptions that different collapse models imply giving up are universal quantum computing, human-level artificial intelligence, and friendliness to human-level AI. So those are the assumptions that collapse models could bring into question. what I call relativist type interpretations like Everett, many worlds, and cubism. I think give up on the idea of absoluteness of human thoughts. Deterministic hidden variables such as Bohmian mechanics, which have an explicit sort of non-locality built into them, giving up on the relativistic causal arrow. And then finally, there are super deterministic theories which give up on the free choice, give up on the interventionist causation idea. But then I wanted to highlight this one because I think there are many physicists who say, believe with the slogan that, quantum theory needs no interpretation. And if you ask those physicists, do you believe in, free choice, to put it simply? Do you believe in relativistic causation? Do you believe right? They're likely to answer yes to all of those things. And that means that actually they don't, right? They're wrong. They don't have an interpretation. Quantum theory does need an interpretation. You have to think about how it responds to how your favorite way of thinking about quantum theory responds to the local friendliness no-go theorem. Okay, so I promised you a bit more on the collapse interpretation. So one, and again, this was mentioned by Adrian Kent, at least, promoted most recently by David Chalmers and Kelvin McQueen, the idea that thoughts necessarily lead to collapse, or consciousness necessarily leads to collapse. So in this type of theory, what are we giving up here? Well, he would actually say that if qualia is actually having thoughts, human-level thoughts, if you look at the theories that they propose, that would mean that it would be impossible to put qualia into a superposition of logical states corresponding to different thoughts. But we know that if universal quantum computing is possible, then we would be able to do that. We can write down, in principle, we can write down a program which would put qualia into that superposition simply by feeding in a qubit that he's supposed to look at in a superposition or an entanglement, rather. Well, either, right? So, in other words, what this interpretation, this type of collapse means that universal quantum computing would be impossible. And that's obvious. That would be an incredible discovery to make by doing this experiment, that we can actually cause collapse of the wave function by doing a particular type of quantum computation. I don't think it's a likely thing, but we can't rule it out. And so I think that's one motivation. Okay, second type of collapse model is one proposed by Roger Penrose and some of his colleagues. And according to him, human-level intelligence itself arises from some sort of what he calls an orchestrated collapse, which is some sort of objective reduction process, a collapse of the wave function involving, it's an uncomputable process. It involves some biology, plus quantum, plus gravity. So it's something that we can say very little about, except that he thinks that this is actually essential to human-level intelligence. So we've evolved to be able to make use of this, to have the sort of human-level thoughts which we have. So in Penrose's opinion, a human-level artificial intelligence, by any digital algorithm that is, an algorithm which is obviously computable, right, because we're literally computing it, that would be impossible. So we're just never going to achieve human-level artificial intelligence, according to Penrose. Now, I think this is going to be challenged in the pretty near future, but that was his point of view. Okay, and then finally, the most well-known type of collapse theory, what's called spontaneous collapse theory, which as I'm sure you've heard people talk about. I'm going to be specific here and say spontaneous collapse with a primitive ontology. That's a technical term to basically mean that you have to tell me that there's something happening in space-time. There are events happening in space-time. So Garadi, Rimini, and Weber, the most famous example of this type of spontaneous collapse theory. You probably had people tell you about this already, that you have these two parameters, lambda and alpha, and you get collapse of the wave function as if there were measurements happening on each individual particle. And so you can think of whenever a particle collapses like this at some random time with rate lambda, that causes a flash in space-time, like not a literal flash of electromagnetic radiation, but think of that as being that's the actual event in space-time that correspond to the ontology of the theory, so that we have an ontology in space-time, not like in Hilbert space. Now, you might think, oh, well, collapse is going to prevent universal quantum computing, because you can't do universal quantum computing, because you can't make, collapses cause superpositions to collapse down to single branches or whatever, and so you could not do universal quantum computing. But that's not true, okay? So these collapses actually do not prevent universal quantum computing, because the way they act is essentially the same as any types of error in a quantum computer. So we know that a fault-tolerant quantum computer can correct for errors, right? There are all sorts of things that cause errors in quantum computers. This would just be one more of those things. And so it would just get error corrected away. We'd never even notice that it existed. So in this theory, this spontaneous collapse theory, there would be collapses happening, but those collapses wouldn't have anything to do with the actual information in the quantum computer, because that's the way that error correction works. They're just going to be purely random. So the quantum computer would have these flashes, right? The ontology would be, well, flash, 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 flash. But there's nothing, you can't, from those flashes themselves, there's absolutely nothing in there about the thoughts that the quantum computer running the artificial intelligence algorithm would be having. So in other words, unlike in the human brain, right, where the collapses would actually, where these flashes would be correlated with things moving around in our brain and whatever we're thinking, this just wouldn't be the case for a quantum computer running an artificial intelligence algorithm. And so the assumption that human-level artificial intelligence has the reality of the thoughts of a human-level artificial intelligence is like, to go back to exactly what my phrasing was, right, that the thoughts are as real as any thought of a human, just would not be the case, right, because they simply would not have an ontology in the theory, unlike the way that human thoughts would have an ontology. So that assumption would just be false according to that theory. Okay, so to summarize then, yeah, so the general idea is that we have metaphysical assumptions that can have falsifiable empirical consequences in conjunction. If we put together the right metaphysical assumptions, we can derive, for example, these inequalities, and they can be falsified in an experiment, and so we can say, in the case of Bell, that has already happened. And what I'm suggesting is that the new frontier in this field of experimental metaphysics is through continued advances in AI and quantum computing, and that we'd be able to rule out these metaphysical assumptions here, which are collectively, yeah, this is the thoughtful local friendliness set of assumptions. And as I said, so either one of these two technological assumptions or one of these four metaphysical assumptions must be false. Okay, so just to end on a future direction, so as I said, so I very briefly talked about an experiment which we did with a single qubit friend. We could think of this as being the first step on building a big quantum computer to act as our friend, but we could also think of it as being or maybe not the first step, the 0th step, as I said. We could also think of it as the 0th step in any number of other ways we could think about defining a friend. So, for example, in terms of being macroscopic, redundant encoding, some other sort of classicality. I won't go through all the list of all these things, but just to say that there are many other directions that one could take these experiments other than in the direction of a human-level artificial intelligence. And with those other, yeah, I think there's also a lot more theory work to be done as well by considering those different directions. Okay, thank you very much.
Thank you, Professor Howard Wiseman, for this wonderful talk and also finishing it in time. So now we shall go for the second talk of this session, which will be of 45 minutes. And after that, we shall go for a coffee break, and after that, we shall have a discussion. So, yeah. So
So do I need to do anything apart from...
we'll take care of it. So you please stay online.
Yeah.
Yes, so the discussion will start after the coffee break, and it would be 11:30 a.m. Indian time. Yeah. Yeah. So our... is this? Okay, so our next speaker is, he's already acquainted to our audience. We are interacting with him since last 2 days. So we have, for the second session, Professor Tejinder Singh. He's a theoretical physicist working in the field of quantum gravity and cosmology, mathematical physics, quantum measurement problems, and foundation of quantum mechanics. He has been a faculty member in the Department of Astronomy and Astrophysics in the Tata Institute of Fundamental Research from 1989 till 2022. Currently, he is affiliated to Inter-University Center for Astronomy and Astrophysics, known as IUCA in Pune, India, as a visiting professor since 2023. So I request Professor Singh to start his talk. Thank you.
Thank you, Manabendra, for your kind introduction, and a big thank you to the organizers for organizing this very important conference. Thank you all for taking part so actively, especially the younger participants, and thanks to the organizers for giving me an opportunity to present these ideas. So this is how I titled the talk, Quantum Foundations, a Gateway to Quantum Gravity and Unification. So this is my list of the foundational problems of quantum theory. Collapse of the wave function and absence of macroscopic superpositions seems to contradict the Schrodinger equation and asks for an explanation. The Schrodinger equation is deterministic. Initial conditions are precisely prescribed, and yet the outcomes of measurements are random and unpredictable and obey the Born probability rule. The puzzle of quantum non-locality, how correlated quantum systems manage to influence each other outside the light cone. Supraquantum or superquantum non-local correlations are allowed by special relativity. Is that a contradiction between quantum mechanics and relativity? And to me, perhaps the most important problem, which is not talked of much, the so-called problem of time in quantum theory. What is the problem? One can assume classical space-time in quantum theory only if the universe is dominated by macroscopic classical objects. Here by classical space-time, I mean both the gravitational field as well as the underlying space-time manifold, which is described by points which are described by real numbers. To have such a space-time manifold, the universe should be dominated by macroscopic classical bodies like our universe today is. But that need not have to be the case. Low energies don't imply classicality. We know that. We see quantum systems at low energies. Now, because these classical objects are a limiting case of quantum theory, it follows that the theory depends on its own limit in assuming the existence of classical time. Hence, if we were to remove classical objects from the universe at low energies, we should still be able to do quantum theory, even though we don't have classical time. So this is the so-called problem of quantum time in quantum theory. Look for a reformulation which does not depend on classical time. That will also be one of the themes, the major themes to be addressed in this talk. And interestingly, it turns out that if we try to develop some formalism which addresses these quantum foundational questions, it also guides us to a theory of quantum gravity and of unification of the forces. So this is the plan of the talk. One possible dynamical model for collapse of the wave function, essentially collapse models, which you have already heard about. And the second part, what is responsible for the phenomenology of collapse models, a possible theory underlying dynamical collapse, Stephen Adler's theory of trace dynamics. Trace dynamics does not incorporate gravity, quantum gravity. So one possible idea of how to include quantum gravity in trace dynamics, which I call generalized trace dynamics, and related how to remove classical time from trace dynamics, how to remove the space-time manifold by using non-commuting numbers, quaternions and octonions, and how that guides us to unification of forces. Okay, so part one, a dynamical model for collapse of the wave function. Assume that lifetime of a superposition is not infinite but finite. So quantum theory assumes superposition lifetimes to be infinite. We relax that assumption. We say that if you take an elementary particle, a nucleon, neutron, or a proton, a superposition of position states of such a particle spontaneously localizes to a width RC once in a very large time, capital T, which is equal to 1 over lambda, where lambda is the rate of collapse. So as you know, in collapse models, GRW, CSL propose testable value of the collapse rate, lambda, 10 to the minus 17 collapses per second. In other words, capital T is of the order of the age of the universe, 10 to the 17th second. And again, phenomenology assumption that the collapse size is around 10 to the minus 5 centimeters. Both these numbers should be tested by experiment. The beauty of collapse models, as we saw, is that if you have a quantum system with n entangled particles, the collapse rate amplifies to n lambda, and if n is 10 to the 23, it means you will have 1 million collapses, like for a macroscopic object, 1 million collapses per second, and that is what is, or one collapse every microsecond, and the collapse of one particle collapses the entire macroscopic object because of the entanglement. So this is how we understand absence of macroscopic superpositions and collapse of the wave function during a quantum measurement because of this enormous amplification of a very tiny rate of spontaneous collapse. Mathematically, as you saw in Henrik's talk, this is modeled as a stochastic, nonlinear, non-unitary, but norm-preserving modification of the Schrodinger equation, and this is being tested by experiments, right now neither confirmed nor ruled out. And as we saw, collapse models are non-relativistic, and my picture is that if you have to make a relativistic collapse model, we must raise time to the status of an operator and have spontaneous collapse in time as well. And something else will play the role of a classical time parameter. The standard time coordinate is on the same footing as the spatial coordinates. So we make space-time coordinates into operators, and we have something else playing the role of a time evolution parameter. So let us now start to ask this question. What is the fundamental origin of the phenomenology of collapse models, of spontaneous collapse? And what we will start by asking is what is the difference in the role of, what is the difference in the, sorry, which way am I headed? Right. What is the difference in the role of randomness or stochasticity and non-unitarity? So there are two things happening in collapse models. We are invoking a norm-preserved non-unitarity that is responsible for non-linearity, and we are invoking randomness. So randomness and non-unitarity are invoked together in the CSL model. We want to start by asking what is their relative significance, what is non-unitarity doing, and what is randomness doing. So to answer that question, we first made a simple model, two-state models. Suppose we are interested in a generalization of the Schrodinger equation described by having the following Hamiltonian H. It is H cross omega into H naught plus I gamma A. Gamma is a real coupling constant. It could be positive or negative. A is some observable. Now this total Hamiltonian is not self-adjoint, and the evolution of the state vector phi is hence non-unitary, and also it does not preserve norm during evolution. Let us insist on norm preservation and define a physical state psi by dividing phi, ket phi by its norm, so that evolution of psi is norm preserving. Then if phi describes if phi obeys Schrodinger evolution, psi will obey the following nonlinear equation, where A wedge is the expectation value of A in the state psi, and the corresponding master equation is shown in the last line. Interestingly, this is a nonlinear master equation. It's not of the Lindblad form, so it will allow signaling, but we'll take care of that. So let's leave it at this for a moment and see what kind of evolution happens in such a system. So as I said, we want to find the impact of a norm-preserving non-unitarity. We have not switched on randomness as of yet. So consider a two-level qubit system with H naught rho A as 2 by 2 matrices, and let us write these matrices in the eigenbasis of A, assumed to have two real eigenvalues, lambda naught and lambda 1, and then here's a matrix expansion of H naught of the density matrix rho, where x, y, z form the block vector. A is, so we are in the diagonal basis of A. These are the density matrix evolution equation splits into these three equations for the time evolution of x, y, and z. In the limit in which gamma by omega is much greater than 1 or much less than -1, these equations simplify. The solution is shown here, and when gamma is much greater than 1, one is driven to the eigenstate 0 of A. So this is, and if gamma is much less than 1, one is driven to the eigenstate 1 of A corresponding to the two eigenvalues. So you start with a superposition, but this non-unitarity, when it is significant, is breaking superposition. So we have a non-unitary, norm-preserving Schrodinger evolution, and in certain circumstances it can break superposition. So conclusion, deterministic, non-unitary, norm-preserving evolution can lead to breakdown of superposition when the non-unitarity is significant. Now what about the origin of randomness? The claim is that the origin of randomness is a coarse graining. Assume the non-unitary deterministic theory to hold at some time resolution tau, at which quantum theory has not yet been tested. We ask what is the emergent theory when coarse graining is done to some time scale t, which is much greater than tau. Then, if the anti-self-adjoint coupling gamma is negligible, the emergent theory is quantum mechanics with the self-adjoint Hamiltonian. If the anti-self-adjoint coupling gamma is significant, interpret gamma as a measure of coupling with the measuring apparatus. Randomness in gamma arises, this is one possibility, because time of arrival is not being measured to resolution tau. Your resolution is poorer, it is some time t, but depending on when you arrive within the time interval, gamma could be much greater than 1 or gamma could be much less than 1, but you would have smeared over both those possibilities, and because of coarse graining in time, outcomes appear random even though the outcomes are deterministic in the underlying theory. So to summarize, non-unitarity is responsible for breakdown of superposition, but that breakdown is deterministic. And randomness arises because of ignorance of the underlying theory, because we are observing at a lesser level of precision. So we can try to motivate how to derive CSL from the simple model that I described to you. We don't really have to go into this right now. It's just that we have to model randomness by mapping the coupling constant gamma to, say, a Wiener process as in the CSL model. And then with certain assumptions, this is preliminary, we can map the nonlinear Schrodinger equation that we had to the CSL model that Henrik showed you yesterday and which we discussed. The corresponding master equation for this randomized Schrodinger equation is of the Lindblad form. So in the emergent theory, there's no signaling. And so let's skip this part. I hope you get the picture. And this is the conclusion from this part of the talk. Quantum theory is an emergent approximation to an underlying deterministic theory which is non-unitary but norm-preserving. Randomness arises because of coarse graining over the time of arrival. That is one possible source for randomness. Some kind of coarse graining is definitely involved. Okay. So now we want to make these ideas of, so we have some idea what is the relative role of non-unitarity and of randomness in collapse theories. Right. So, but we want a better understanding of collapse models, underlying theory for collapse models, which is something more formal than the simple model that I showed you, and that is the Adler's theory of trace dynamics. So what is the theory? Conventional quantization in the Heisenberg picture proceeds by looking at a classical Hamiltonian dynamics, raise classical dynamical variables to the status of matrices / operators, replace Poisson brackets by Heisenberg commutation relations, and replace Hamilton's equations of motion by Heisenberg equations of motion. That is canonical quantization in the Heisenberg picture. Adler's idea in trace dynamics is let's raise classical dynamical variables to matrices, but do not impose Heisenberg commutation relations a priori on these matrices. Instead, construct a Lagrangian / Hamiltonian dynamics with matrix value dynamical variables. So let us see that with an example. Suppose you have a classical set of classical particles Qi, for which we write the action principle is just the Lagrangian is the kinetic energy. Now what we'll do, these real numbered value dynamical variables Qi are raised to the status of matrices. A bold Q is a matrix. Your Lagrangian now would become a matrix polynomial, but we want it to, the action to be a scalar. So take a matrix trace of the polynomial formed by these matrices dqi by d tau whole square. So that's the origin of the name trace dynamics, because the Lagrangian and the Hamiltonian are a trace. By varying the action with respect to matrix valued variables, we can derive equations of motion. In this case, it would be just simply qi double dot equal to 0, but it's now a matrix equation. But interestingly, it turns out this is already a pre-quantum theory. It is as if we were doing classical dynamics, but just the act of working with the matrices makes this into a pre-quantum theory, because we do not impose any commutation relation on the Q's and P's. The Q's don't commute with each other, the P's don't, and the Q's and P's don't commute with each other. But there is a very remarkable conserved charge, which is what makes this into a pre-quantum theory. You notice that the Lagrangian is a trace, so you can make unitary transformations of the variables inside, and the trace will not change because of cyclic permutations of the unitary operator, the trace will remain unchanged. And the same for the trace Hamiltonian, it is invariant under global unitary transformations. Noether's theorem then gives a new conserved charge shown here. Look at its structure. is sum over all degrees of freedom, the commutator Q times P, where B stands for bosonic and F stands for fermionic. I did not define how bosonic and fermionic degrees of freedom are defined, because that's not too important right now. The commutator of Qp for bosonic minus the anti-commutator of Qp for fermionic summed over all degrees is a conserved quantity, where P is the canonical momentum corresponding to Q. That would follow from variational principle. Qp is just del L by del Q dot. So look at the structure of this quantity. It has dimensions of action, but each commutator is not individually IH bar. It's just the sum of commutators which is conserved. But so this is what makes trace dynamics into a theory more general than quantum theory. It has within it the seeds of quantum theory as well as of collapse model. Okay, so we have seen this. Right. So trace dynamics under certain approximation leads to quantum field theory, and under other approximations possibly to collapse model. So quantum theory is an emergent phenomenon in trace dynamics, which is a Lorentz invariant matrix valued Lagrangian and Hamiltonian dynamics. It is deterministic, non-unitary, but norm-preserving. In general, the Hamiltonian is not self-adjoint. So like in the model that I just described, assume trace dynamics to hold at some time resolution tau p, at which quantum theory has not yet been tested. Ask, what is the emergent dynamics at a time resolution tau much greater than tau p? There are two possibilities, like in the toy model. In the approximation in which H is self-adjoint, evolution is unitary, and techniques of statistical thermodynamics, conventional statistical mechanics are applied to show that the novel charge that I showed you gets equipartition, and since that sum is a constant and this equipartition, each average commutator is itself a constant. That constant is identified with IH bar. So because of this coarse graining of the time resolution, if the anti-self-adjoint part is negligible, then we recover quantum theory, and Adler shows how Heisenberg equations of motion and quantum field theory emerge in the thermodynamic equilibrium approximation. So this is one limit of trace dynamics. There's a second possibility. If the anti-self-adjoint part of the Hamiltonian is significant, evolution breaks quantum linear superposition. Coarse graining the dynamics introduces an apparent randomness in the evolution because of ignorance, while obeying Born rule, and there's a possibility of recovering collapse models because of the overlying structure of the theory. The underlying theory of trace dynamics, as we noted, is deterministic and non-unitary. If non-unitarity is significant, linear superposition is broken, and upon coarse graining, the emergent theory is either quantum theory or it is classical dynamics. So immediately a question arises, if the underlying theory is deterministic, what happens to Bell non-locality? So I think we can have that in the discussion. Okay, so this we have already discussed in the last 2 days, that if the novel charge is not equipartitioned, if the quantum commutator does not hold, trace dynamics can violate the Cyrillson bound, giving us Bell correlations higher than 2√2 and going towards the PR bound of 4. This suggests, maybe, if we can experimentally confirm this result from trace dynamics, namely that quantum mechanics is an approximation. It's not an exact theory, but in this sense it is approximate. Okay, what are the limitations of trace dynamics? It does not specify any fundamental Lagrangian for the universe. It's a pre-quantum theory. It's not a pre-space-time theory. Space-time is given as Minkowski. It's flat. It's classical. It's assumed classical and flat, no gravitation. but this is an intermediate step towards developing a pre-spacetime, pre-quantum theory, which is what we are interested in. We want to remove classical time from quantum theory, and trace dynamics is a possible formalism for doing that, provided we figure out how to include a matrix-valued gravitation and a non-commutative pre-spacetime. So we are going to replace real number-valued spacetime by a non-commutative pre-spacetime, and also propose a fundamental Lagrangian. In so doing, while addressing the time problem in quantum theory, we are also led to a candidate theory for quantum gravity and for unification of fundamental forces. It's still work in progress. No claim is made that this task has been completed and that this is the right way. It looks interesting, that's how I would put it. And we'll call this generalized trace dynamics because we are now going to include gravity and remove classical time. So how is that done? To do so, we must find a good set of classical variables which describe gravitation in general relativity and which we can raise to the status of matrices. Like I said, in trace dynamics, classical dynamical variables have to be raised to matrices. That's pre-quantization. So it turns out that the metric of general relativity is not the best way to go to trace dynamics. The metric already is a matrix, so we would have to take each component of the matrix-valued metric and raise it to a matrix. It doesn't work well, but there's a very interesting way out due to something known as the spectral action principle of Chamsuddin and Kohns, shown in the first line. So on the right is the Einstein-Hilbert action of general relativity. LP is Planck length. What these authors showed, along with others, that given a curved space-time manifold, which has gravitation, let's write the Dirac equation on such a curved space-time manifold on which a metric is given. Solve the Dirac equation, find its eigenvalues lambda I, and there's this beautiful result that the Einstein-Hilbert action is the sum of the square of the eigenvalues of the Dirac operator. So on the right-hand side, your sigma I lambda I squared. That is the Einstein-Hilbert action, written on the left in compactly as trace of LP squared D squared, where D is the Dirac operator. So this amounts to saying that the lambda I are observables of general relativity. They describe gravitation in the same way that the metric describes the gravitational field. Lambda I also describe the gravitational field, and for various reasons, it helps to work with these lambda I as variables which will be made into matrices. So each lambda I is raised to the status of a matrix lambda I hat, equivalent to QB dot I. That's the definition of QB dot, the trace dynamics variable. So you see, we call this object an atom of space-time. And what will its trace dynamics action be? It will be trace of QB dot square integrated over a time parameter d tau known as Kohns time, because they are going to get rid of classical time. That will also become an operator. So this is not the time coordinate. It turns out now that we are in the domain of a non-commutative geometry, because the variables are being metricized, made into operators. Non-commutative geometry allows a new notion of time known as Kohns time, which plays the role of a time parameter measuring evolution. Right, so as I said, each matrix, each eigenvalue has been raised to a matrix. Which matrix, which operator? Same as the very Dirac operator of which it was an eigenvalue. So atoms of space-time are a collection of Dirac operators. Classically, on the classical manifold, there's only one Dirac operator, but in the trace dynamics, in the generalized trace dynamics, there is one Dirac operator per eigenvalue. The same principle, Shamsuddin cones, can be generalized to include fermions indicated by this symbol QF. It can be further generalized to include Young-Mills fields indicated by the symbol QB, and one can construct a trace dynamics Lagrangian for Young-Mills field, and this is what we call one atom of space-time matter, which includes an elementary particle like an electron along with all the bosonic fields that it is producing. So think of QB plus QF as an atom of space-time matter, and the universe is made up of enormously many copies of such space-time matter atoms. And this is in general a Hamiltonian which is not self-adjoint, the resulting Hamiltonian. Whenever the anti-self-adjoint path is significant, that can lead to spontaneous localization, giving rise to the classical theory that we know, general relativity and the standard model fields. So this is now a pre-quantum, pre-spacetime theory in which gravity has been made into quantum gravity. Quantum gravity information is in these variables QB dot. The Young-Mills fields for the standard model, that information is in these fields QB. Now we are left with one more step. We have to remove time and space-time. We have not done that yet. Okay, so this I can skip. Given that Lagrangian, one can write the equations of motion, and one can write the Lagrangian in a very nice, simple form shown in the last line. You will recognize this immediately as kinetic energy. So in a subtle way where we combine bosons and fermions together, what you are left with is that the action principle for an atom of space-time matter is nothing but our old friend kinetic energy, except that these are operators or matrices. You have to take the trace. And another interesting thing to note is that there are only three fundamental constants here: Planck's constant, Planck time, and Planck length. Instead of G, H bar, and C, we are using H bar, Planck time, and Planck length, which is equivalent. The ambition is that all other fundamental constants of the standard model should now be derived just from this action. This is action for one atom, and if you add it over all the atoms, you get the total action for the universe. And no further fine-tuning is allowed. Everything else should follow from here, provided we have some way of saying what are we going to do with how much time do I have? 7 minutes. Okay, all right. So this is the last part of the talk. We are going to get rid of real numbers, space-time background, and we ask this question: what do numbers have to do with elementary particles? Answer: making physical space with numbers other than real numbers. There's nothing sacred about real numbers. In a pure quantum theory in which there's no classical bodies dominating the universe, we'll make pre-space-time with quaternions and octonions. And because they are non-commuting numbers, the original problem of allowing a commuting space-time in quantum theory will now be gotten rid of. The contradiction was between quantum systems which obey superposition and an underlying space-time whose points are commuting and don't obey superposition. That contradiction is resolved by labeling pre-space-time by numbers which don't commute, like the quaternions and octonions. There are only 4, so this is the motivation. There are only 4 kinds of number systems which allow these basic operations. These are known as division algebras, and these are, as we know, these are real numbers, complex numbers which describe rotation in a 2-dimensional plane. This we all know. And as you know, Hamilton was interested in this question: which is the number system for describing rotations in 3 dimensions? And obviously the original guess is that that number system may be 3D, add one more imaginary unit to the complex number, turns out to be not like that. You have to double the dimensions 1, 2, 4, and you need quaternions with this definition to describe rotation in 3 dimensions. And there's only one more division algebra, so this we can skip. There's only one more division algebra, the octonions. Again, the dimensionality is doubled from 4 to 8, 1, 2, 4, 8. And there are now 7 imaginaries, each of which square to -1, they anti-commute. And this so-called Fano plane gives us the multiplication table for the imaginary directions of the octonion. In quaternions, multiplication is non-commutative but associative. Here it is non-commutative and non-associative. Okay, and of course we know real numbers are used to describe the line and 3-dimensional space. Quaternionic space, quaternions can be used to describe the 4-dimensional space-time of special relativity. What gets interesting is that when you go to the next level, the octonionic space, then you cannot put fermions with arbitrary values of charge and mass. The algebra of the octonions constrains properties of the fermions that you put on the space-time. So octonions describe the unification of space-time and the internal gauge symmetry space of gauge theories. And these 5 exceptional Lie groups, which are symmetry groups associated with the octonions, all play a central role: G2, F4, E6, E7, and the largest one, E8. G2 is the automorphism group of the octonions. It's a 14-dimensional group. And the connection to particle physics is that starting with, say, complex octonions, the complex quaternions, we can make Clifford algebras from which we can make spinors. And these spinors have symmetry properties associated with the standard model. The subgroups of these exceptional Lie groups coincide with the standard model subgroups SU3, SU2, SU1, and U1. The connection with the Dirac operator is very interesting. If you take the 3 imaginary directions of the octonion, of the quaternion, and make this gradient of the typo in the first term, there's no del I by del x. It's just I hat del by del x plus j hat del by del y, and so on. Just take the square of d, and you get the Laplacian. So it is said that the Dirac operator was actually first discovered by Hamilton. It is that Hamilton knew this, but we didn't know what to do with it. It is this object and its generalization to octonions which plays a central role in understanding why the Lagrangian of the theory is trace d squared. So the variables q dot that I showed you is actually nothing but the Dirac operator in octonionic space. So in generalized trace dynamics, when we remove space-time to include a non-commuting pre-space-time, which is consistent with quantum theory, you would write, for example, an action like this, where the matrix has matrix-valued components over different directions. So in Newtonian mechanics, if you have a position variable q, is qxi plus qij plus qzk. All we are doing here now is making those q's into matrices, and those matrices are nothing but components of the Dirac operator constructed as a gradient operator on the octonionic space. Now I don't have time to go into it. If we assume a so-called E8 cross E8 symmetry, it can be shown that the Lagrangian that I described for you can describe the standard model, general relativity, and 2 new forces, 6 forces in all, 4 that we know, 2 that are new. And this is the big picture. I'll end within 2 minutes. Collapse of the wave function is very important because collapse is what gives rise to classical real number valued spacetime from pre-spacetime. Collapse is very central. It's not just something that happens during a measuring apparatus. It's happening all the time according to spontaneous collapse. Spontaneous collapse is what keeps macroscopic objects classical, like stars and galaxies, and in turn gives rise to space-time. Classical space-time arises from collapse of the wave function. At the time of Big Bang, there were a very large number of atoms of space-time matter. The theory obeys E8 cross E8 symmetry. At the electroweak symmetry breaking, the universe splits into this structure that is shown here. We find space-time is actually 6-dimensional with 3 space and 3 time directions, which is a possible explanation for the puzzle of quantum non-locality. There are additional time-like directions through which one can travel in a local way, and effectively that appears like non-locality in our universe. So the 6D space-time splits into 2 copies of 4D space-time, ours with a signature 1 time and 3 space, and the other one with 3 times and 1 space, with 1 space and 1 time direction overlapping, so that in all it's a 6D space-time 3-3. And from the gauge theory point of view, these 2 additional time-like directions become internal symmetry. The internal gauge symmetries are equivalently time-like directions of a second 4D space-time, which is also a part of our universe. And there are some predictions for experiments. There's no smoking gun prediction yet, but there are some of these ideas. One thing I forgot to write here is that gravitation violates parity, same way as weak interaction violates parity. Only left-handed particles take part in the weak force. Only right-handed particles take part in gravity or in pre-gravity, which is the SU2R gauge theory. So the weak interaction and general relativity are 2 facets of an underlying unified force, which we might call gravi-weak unification. So going back, so we see that we are able to say something useful about these foundational problems of quantum theory in the overall framework that I think Nicholas called doing good physics. So I hope this is good physics. We are not talking in the air. We are looking at a bigger picture of involving the various interactions of fundamental physics. And this is my last slide. Let's see what has happened. So we are concluding that gravitation and quantum theory both are emergent phenomena. Let's go back to what happened at the beginning of the 20th century. Newtonian mechanics was generalized by Einstein and others to special relativity, and by Einstein to general relativity. Newtonian mechanics was also generalized in another way, special relativity and then quantum theory. I imagine that maybe Newton comes back to life once again, maybe meets Einstein and the founding fathers of quantum mechanics, and suppose he knows everything that we have learned since the beginning of the 20th century, in this last century, trace dynamics, non-commutative geometry, collapse models, application of octonions to particle physics, and Newton says, okay, he would do it differently. From special relativity, let us set up a matrix-valued Newtonian but relativistic dynamics on a non-commuting pre-space-time. Replace Newton's dynamical variables by matrices. That already takes us to quantum theory. And replace the real numbered valued Newton space-time by non-commuting pre-space-time labeled by the octonions. Make a Lagrangian using the Dirac operator, which is the octonionic gradient operator. The Lagrangian is trace d square. So we are children of Newton. We are really doing Newtonian dynamics in a very sophisticated way with matrices and octonions. But in so doing, you see that we already have gravity because we have trace d squared. D includes information about gravity. We have other forces, again that is in the Dirac operator. We have fermions, that's also in the Dirac operator. Given this pre-theory, pre-quantum pre-spacetime theory, spontaneous collapse gives rise to classical spacetime and to classical objects and classical fields. Collapse is important not only for explaining macroscopic classicality, it is also important for explaining where does classical spacetime come from. And those degrees of freedom which have not collapsed, they continue to obey either the generalized trace dynamics or quantum theory. So hopefully this is a possible way ahead in understanding the foundational problems of quantum theory, which may have an impact on particle physics and quantum gravity. Thank you very much for listening.
Thank you very much, Professor Singh, for this interesting talk. So idea is that now we will go for coffee, and following that we will have our discussion session. So at 11:30, yes, so at 11:30 we will again assemble back here and start the discussion. And if you have some question, please register your name to Professor Ritesh Singh, and then during the discussion session we will call up. Thank you very much.